Okay, and without further ado, I'll introduce the first speaker of this afternoon session, who is Miroslava Dessauges-Zavadsky, who will talk about a high-redshift clumpy galaxy from the lensing perspective. So please, yeah.
Hey, hello everybody.
Yeah.
I hope you can see my screen and hear me.
Yeah,
okay.
We can hear you very well.
Thank you very much. I would like first to thank the organizers to give me the opportunity to present you my work on high-redshift clumpy galaxies, the lensing perspective. And I would like first to remind what we have heard already during this conference, that the rays frame UV and optical images reveal that galaxies around the cosmic star formation peak have perturbed morphologies characterized by UV bright star-forming clumps for about 60% of galaxies, as illustrated in this figure. The study of these star-forming clumps is important for several reasons. First, it could help us to determine how galaxies assemble their mass and what is the role of mergers with respect to the secular evolution. Different scenarios for clump formation have indeed been proposed. They could be either remnants of satellites that merged with the host galaxies, or they could have been formed in situ in host galaxies and contribute to the secular evolution of the host galaxy. Second, as we have heard in different talks, clumps could contribute to the growth of the bulges if they are long-lived and if they migrate toward the center. Third, determining the intrinsic physical properties of these star-forming clumps might help to understand the star formation process in distant galaxies if these clumps are really formed in situ in the host galaxy. And finally, studying clumps could also help to constrain what is the strength and the role of the feedback at subgalactic scale with respect to the global galactic feedback. So in this talk, I will focus on the following two items: determine how galaxies assemble their mass, and second, understand the star formation process in distant galaxies. So with respect to my first query, we know now that several observational findings do support that most of these UV bright clumps are star-forming regions formed in situ in host galaxies and are not accreted satellite following a merger event. So I would like to review these most important observational findings. So first, the Shibuya et al. 2016 work has shown that high-redshift that the redshift evolution of the clumpy galaxy fraction is inconsistent with the evolutionary trend for both major mergers, shown in red, and minor mergers, shown in green. Then Shibuya also shown compared the distribution of Sersic indices for clumpy galaxies in red and for non-clumpy galaxies in black, which are separated into stellar mass bins here. And I found that clumpy galaxies are dominated by disk-like systems and that show evidence for, do not show evidence for merger process. Third, back to 2017, Elmegrin et al. Have shown that spiral non-clumpy galaxies shown in the left panel and edge-on clumpy galaxies, the so-called chain galaxies shown in the right panel, have comparable d-scale height, favoring also the in-situ clump origin. And finally, as we have heard, the kinematic of the majority of star-forming galaxies at the peak of the cosmic star formation, including clumpy galaxies, is dominated by order disk rotation and not mergers. And indeed, the redshift between 1 and 2, we have about 75%. However, these high redshift rotation-dominated galaxies are very different from their local counterparts. As shown in this figure, they are characterized by much higher velocity dispersions with respect to nearby galaxies, and the physical origin of this turbulent motion at galactic scale is not fully understood. Or gravitational perturbation produced by, for example, high molecular gas fraction, disk instability triggered by intense inflows, or minor mergers. So the gravity-driven turbulence is currently favored with respect to the feedback-driven turbulence. And a simple modeling of the gravity-driven turbulence following the Thumre stability criterion gives an expression for the velocity dispersion, which depends on the rotation velocity, the molecular gas fraction, and the critical Thumre Q parameter, which is equal of 1 for quasi-stable gas disks. So when we plug in the molecular gas fraction evolution with redshift, which is rising between redshift 0 and 3, we find a velocity dispersion rise with redshift, shown here by the gray shaded area in the left panel, which really nicely reproduces the velocity dispersion measurements of high redshift galaxies. And this suggests that the gravity-driven turbulence is mostly induced by high molecular gas fraction. So such high velocity dispersion yield the marginal stability of these high redshift disks with ratio of rotation velocity over velocity dispersion, which is approaching 1 toward higher redshift. So the question is, do the high gravity-driven turbulence associated with disk instability imply the fragmentation of these disk-like galaxies? And could this fragmentation then produce the formation of massive gas clouds that will turn into the star-forming clumps we see? So based on simulation, as we have also heard during this conference, it has been proposed that high redshift turbulent disks do indeed fragment to form in situ gravitational bound gas clouds believed to be progenitors of the observed stellar clumps. So here I show the time snapshot of the fragmentation process of a typical high redshift disk with a stellar mass of 4 times 10 to the 10 and the gas fraction of 50% from the simulation of Valentina Tamburello and Lucio Mayer. And in these density maps, we see the fragmentation process produces the formation of gas clumps in red, which survive over a few 100 million years. So shown in the histograms in the bottom panel, the predicted stellar masses of these clumps formed through disk fragmentation range typically between 10 to the 7, 10 to the 8 solar masses, and clumps with masses larger than 10 to the 9 are large. So what are the physical properties of the observed high redshift clumps? So UV bright stellar clumps were mostly believed to be very massive with a median stellar mass between 10 to the 8 to 10 to the 9, shown by the cyan histogram, and with kiloparsec sizes. However, this initial paradigm had to be revised when considering strongly lensed galaxies in which we achieve sub-kiloparsec spatial resolution, but also when a deep sensitivity threshold is applied for the clump selection, like in the Hubble ultra-deep field images. And the compilation of clumps hosted in lensed galaxies, seen here by the green histogram and in the HUDF shown by the red histogram, reveal really a clump stellar mass distribution shifted by 1 to 2 orders of magnitude to lower masses, reaching a median mass of 10 to the 7. And this shift in the clump distribution illustrates both the effect of clump blending in scarce spatial resolution, but also the even stronger effect of the sensitivity limit of the images used to identify the clumps. And what is interesting is that the revised clump masses end to be in very good agreement with the predicted stellar mass distribution of clumps produced in simulation shown here by the blue histogram resulting from disk fragmentation. However, what is very important is that most of these high redshift clumps still remain 10 to 100 times more massive than local star clusters as shown by the yellow histogram. So when constraining the stellar mass function of star-forming clumps between redshift 1 to 3, we find that it follows a power law with a slope of -2. And this is characteristic of the mass function of local star clusters and H2 regions that are hierarchically organized from parsec to kiloparsec scales. And this expectative turbulence-driven fragmentation is the mechanism responsible for clump formation. So this provides really a strong support for the identified clumps in high redshift galaxies to be really scaled up star-forming regions of local star clusters and H2 regions. So to further investigate the physical properties of these high redshift stellar clumps, we considered as ideal laboratories two strongly lensed galaxies at redshift 1. So we first analyzed the cosmic snake galaxy, which is a strongly lensed galaxy producing 5 multiple images. There is the isolated counter image in the north and 4 counter images in the cosmic snake arc toward the south. So the isolated counter image is uniformly lensed and it shows the real morphology of the source galaxy, while the cosmic snake arc provides a zoom in on the internal structure of the galaxy, and there one benefits of very high amplification factors larger than 50 to 200. So together with the lensing model accuracy, one achieves physical scales of 30 to 70 parsec in this redshift 1 galaxy. So the cosmic snake is a typical main sequence galaxy with a stellar mass of 4 times 10 to the 10, a star formation rate of 30 solar mass per year, and with a molecular gas fraction of 25%. This is a rotation-dominated galaxy, and we have been able to identify 21 stellar clumps in the JWST 390 filter. This 5 to 1 galaxy, which is strongly lensed by the Abel 5 to 1 cluster, producing 5 multiple images. There is also the isolated counter image in the north and 2 main counter images in the A521 arc toward the south. The magnification factors over the arc are a bit smaller than over the cosmic snake arc, but together with the lensing model accuracy, which is a bit better here, of 0.08 arc second, we reach comparable physical scales of 30 to 100 parsec in this redshift 1 galaxy. So A521 is also a typical main sequence galaxy with, in fact, very similar stellar mass, star formation rate, and molecular gas fraction to the cosmic snake galaxy. It is also rotation dominated, and we were able to identify 17 stellar clumps in the JWST 390 filters. So what are the physical properties we infer for these clumps in these 2 strongly lensed galaxies? So we see here that the detected clumps in the 2 strongly lensed galaxies have stellar masses between 8 to 10 to the 5 and 3 times to the 10 to the 8. And when comparing the masses of the clumps identified in the cosmic snake arc and the counter image, which are shown here by the green open squares, we find that in presence of a better spatial resolution, the median stellar mass of clumps is 5 times lower than in the counter image. The clumps account in both galaxies for about 15% of the total stellar mass. If we look at the clump radii, those range between 35 parsec and 300 parsec in both galaxies, and they are on average 3 times smaller than in the counter images. And this goes in line with the recent results from Mestrich et al., where they found a clear dependence on the clump radius with the clump magnification after analyzing over 100 clumps. But what is very interesting is that the clump stellar mass seems to reach a low mass threshold around 2 times 10 to the 5, whatever the clump magnification, which is in fact comparable to what we find in the cosmic snake arc and in the A521 galaxies. And this low mass threshold could eventually correspond to the characteristic mass of the star cluster formed at high redshift. If we now examine the clumpiness, which is measured as the ratio of the galaxy luminosity coming from clumps, we see that it is very high in the res frame UV and decreases when moving to longer wavelengths. The clumpiness in the res frame UV is really tracing massive stars from recent star formation, and that suggests that a considerable fraction of 20 to 50% of recent star formation is taking place in the observed clumps. The redder wavelength trace all the popular galaxy. And finally, if we look at the clump stellar mass surface density, they range between 100 to 10,000 in the cosmic snake galaxy and are 1 order of magnitude lower in A521. But this implies globally that many high-redshift clumps reach the typical mass surface density of local young star clusters, which I remind you have about 1,000 solar masses per parsec square and have masses of 10 to the 4 solar masses within a median size of 4 parsecs. So it is quite impressive given that the high-redshift clumps have on average 10 times larger on average 10 times larger in size, but they still achieve the same very high gas mass surface densities. And finally, we don't find very clear galactocentric trend for the clump. So here we investigated the clump stellar mass surface density, age, and past extinction, which is shown here by the clumps in A5 for the clumps in A521, color-coded according to their different physical properties. And therefore, at least in A521, there is no clear evidence for any clump migration. In the cosmic snake, we do find a few of the most massive and dense clumps located closer to the galactic center, which also seem to be on average older. So we seem to observe a different behavior of the galactocentric trends in these two galaxies. So this brings me to my first conclusions on why studying star-forming clumps is important. We now have clear observational evidence that clumps are formed in situ in host galaxies and that support the secular mass assembly of galaxies. And high-redshift clumps appear to be scaled-up star-forming regions of local star clusters and H2 regions with 10 to 100 times higher masses but comparable stellar mass surface densities while being 10 times larger in size. So therefore, high-redshift clumps can help us to understand the star formation process in distant galaxies and determine if it is invariant across cosmic time. So to tackle this fundamental process, we need to detect the parent molecular gas clouds of high-redshift scaled-up star-forming regions, since stars form in cluster from the compression of giant molecular clouds, and the molecular gas traced by CO emission in nowadays galaxies is known to be indeed structured in discrete cloud complexes, which are the seeds of star formation. So typically local GMCs have masses of 10 to the 4 to 10 to the 10 solar masses and radii between 5 to 100 parsecs. And molecular gas clouds of the high-redshift star-forming clumps, we consider again our two strongly lensed galaxies for which we obtained ALMA CO423 observation at the spatial resolution comparable to the HGST resolution. So the detected CO423 emission is shown by the yellow and white contours in these figures. So we have detected for the first time numerous molecular clouds in the velocity space, counting in total 17 GMCs in the cosmic snake and 14 GMCs in A521. So what are the physical properties of these redshift 1 GMCs and how do they compare to local GMCs? So
you have 2 minutes left.
Comparison, the best of local GMC population. And here in these two figures, I show this different scaling relation. The first one showing the linear dependence of the mass of GMCs on their size, implying a constant molecular gas surface density of about 100 solar mass per parsec square for the local GMCs. And the right figure shows the second scaling relation with the dependence of the velocity dispersion on radius. And the high redshift GMCs are shown by the orange crosses for A521 and magenta crosses for the cosmic snake. And we see that they are offset from the scaling relation and thus are clearly different from the local GMCs. They have higher molecular gas masses by 2 orders of magnitude, and as a result, they have higher gas mass surface densities. by 1 order of magnitude. And they also have larger internal velocity dispersion, which is expected if they are in virial equilibrium, given their larger densities. And indeed, we find that these high-redshift GMCs are gravitationally bound. So variations in the physical properties of GMCs hosted in different ISM environments have already been reported. And here, in fact, we observe that the high-redshift GMCs properties resemble those of GMCs found in local mergers and starburst galaxies shown by the black circles. So together they support the picture where the environment matters on the GMC physical properties. And these dependence on environment, internal velocity dispersion of by internal velocity dispersion of the GMCs, which in fact reflect the internal pressure of these clouds according to this equation, which indicates that the pressure is proportional to the velocity dispersion squared. And as shown in this figure, the dependence of the internal pressure on the molecular gas mass surface intensity shown for the local GMCs by the gray data points here also holds on more extreme local and high-redshift environments and extends over 3 orders of magnitude in surface density. So these larger internal pressures goes in fact along with the 1,000 times stronger hydrostatic pressure measured in the cosmic snake and I521 disk compared to the Milky Way disk. And this is a result of the higher gas velocity dispersion and higher gas and stellar mass surface densities measured in high-redshift disk galaxies. And in fact, this hydrostatic pressure is considered as the first order approximation of the pressure that we have on the boundary of a given molecular cloud. So consequently, given really the harsh ambient interstellar medium conditions that are characterizing the high-redshift galaxies, GMCs at their formation have to have the density and internal turbulence pressure that adjust to the ISM condition to ensure their survival. And therefore, the ISM condition directly drive to the existence of these massive and dense GMCs found in high-redshift galaxies, and which then naturally explain the massive star-forming regions we observe in these galaxies. So the detection of GMCs and star-forming clumps at the same spatial resolution in our redshift 1 galaxies allow to check how first they agree and determine if the star formation at molecular cloud scale is invariant across cosmic time. So first, we see that the detected GMCs are massive enough to be the progenitors of the star-forming clumps we observe. And second, we can estimate the efficiency of star formation in GMCs in a similar fashion as done in local universe from the comparison of the GMC massive and stellar cloud masses. And under the hypothesis that identified GMCs are representative of the parent gas clouds, which gave rise to the observed massive star-forming clumps, we get an efficiency of star formation of about 30% in these high-redshift GMCs, which is much higher than what is measured in local galaxies, on local GMCs of about less than. Since I'm running out of time, I would like to conclude this second part, which which in fact tell us, explain why studying star-forming clumps is important. So if the clumps are tracing the typical star-forming regions of high-redshift galaxies, then they help to understand the star formation processes at high redshift. And what we find is that the detection of massive giant molecular clouds in our strongly lensed galaxies confirm the in situ formation of the massive star forming clumps, and that the formation of these dense and massive GMCs appear to be a direct outcome of the ambient ISM condition prevalent in distant galaxies, like the high hydrostatic pressure, turbulence, and density. And in addition to this high mass GMC formation, the comparison of clump stellar masses and GMC masses shows some possible evidence of a fairly high star formation efficiency in these GMCs at redshift 1 in comparison to local GMC, supporting that the star formation process is not necessarily invariant across cosmic time. And I will stop here with, by leaving my open question with respect to what I have described to you.
Thanks a lot, Mirka. Very nice talk. Let's see if we do have questions. So you can either post in the chat or raise your hand. Let me see. Yeah, Anita.
Hey, Mirka, thank you for the very nice talk, impressive results. You mentioned the lack of galactocentric gradients in your galaxies. I was wondering, how much do you think this depends on the uncertainties in the lensing model and on the differential magnification and stretching in the tangential and radial direction?
We don't think it can matter because really, as I said at the beginning, our lensing model accuracy in terms of spatial accuracy is 0.08 arc second. So this is really at this redshift very small. So we don't think that this could really matter. We still have debate mostly in terms of ages. This was really discussed a lot in this conference also. We have really tested also different photometric modeling because we know that the determination of ages only from broadband photometric can be problematic. But here as well, we think that our age estimate is not accurate enough to say anything, but we do not see any possible place for having much older clumps compared to younger clumps. There is, all of them are between 10 to 100, 200 million years, but nothing which would be much older, which we would find close to the center.
Thank you.
Thank you. Do we have other question? Yes, Mike?
Yes, at the risk of repeating myself from another talk, these clumps are very interesting. And you would think that, as first suggested by Emily, I think 2004, that each clump would have its own characteristic chemical evolution. And indeed, we see something curious in the bulge, these massive clusters like Terzan 5, as in Ferraro's talk. And yet in the bulge, we don't really see signatures that you might expect if these clumps had formed long-lived, highly, say, alpha enhanced stars that might have different levels of extreme alpha enhancement. So that it's fascinating that we see these things at high redshift that really should be forming stars of extremely enhanced alpha abundance, maybe, if that's what we expect. And yet we don't see their signatures at the present day.
Okay, so currently at high redshift, there were no direct measurements of really alpha enhancement, but this is certainly something which hopefully will be possible with ELT, combining ELT and gravitational lensing, where probably we'll be able to probe really individual spectroscopy of these clumps. And this could maybe then answer to your question.
Or maybe with Webb, I suppose, one could try to get, and it's hard, there isn't alpha, there are not really clear measurements of alpha to iron from emission lines. So it would be a good thing.
Okay, thanks. I think we are running a little bit late, so moving on to the next talk by Cristina Chiappini. We will have plenty of time to discuss and follow up this during the discussion. So Cristina, if you want, you can start sharing. And I'll give you 3 minutes warning. Is that fine? I think Cristina is still muted.
Sorry, guys, I am getting there.
Don't worry.
First of all, hi, everybody. I'm coming out here of a disaster week, but let's try this, my best here.
We know we are very
already not starting well.
we are very grateful. We understand the big effort. So Cristina will talk about the chemical evolution of the Milky Way bulge. So you can start whenever you're ready.
Okay.
Thank you.
So thank you very much for inviting me. I'm here out of 3 weeks of COVID, me and my daughter, so it has been not easy. So let's see if I can still speak normally. If you don't understand something, just let me know after. So the title it was given to me was chemical evolution, but my point here is to show some chemical evolution, but we cannot really do chemical evolution without first understanding the populations that are inside the bulge, which we know is a mixing of populations. And we have the data now to start doing that. So that's why it's chemical evolution, but is more the question, is there a node bulge, a spheroidal in the Milky Way? And can we bring new observational constraints to have also insights about the oldest Milky Way stars that are in the bulge region? See how careful I am, I said bulge region. After there was this conference on the bulge in 2018 where I gave this review, and what has changed since the end of 2018? 2018 we did this chemodynamical review, but was just before 2 important things happened, which was the apogee and the Gaia revolution. In some sense, part of this was covered also by the talks before. That is in Zenodo, the talk I gave there. So here, what has changed from 2018 to now? So this was the conclusion from 2018 that we still lack statistical significant samples of individual field stars in the bulge and in innermost part regions of the galaxy, having the 6D phase space information, chemistry, and age. And this was what was preventing us of having a clear picture of how the bulge bar was formed and its connection not only with the inside-out formation of the thin disk, but also with the pristine thick disk and halo. Then we started having this first thing now, thanks to Apogee and Gaia and other surveys as well. So we got 3 important breakthroughs in galactic archaeology in the Milky Way. These are the use of asteroseismology for red giants, which can give very precise ages, but these are few stars in some pencil beams, the astrometry brought by Gaia, and also the apogee DR16, DR17, which finally revealed the innermost region of the Milky Way with high resolution spectrum. So we were hit also by Gaia. So first we developed a spectrophotometric code we call Star Horse, where we first run Gaia. Gaia needs complementary information from other photometric bands to see the 3D distance in the galaxy. And already with DR2, we could see very well the bar in the region, in the inner region, in the density plot. Now we have rerun the Star Horse and we have made all this data public. It's more than 300 million stars with just photometry and Gaia information. So from that, of course, we cannot say much in the very inner parts of the galaxy, but there we have now DR16 and DR17. And as I said, in some pencil beams, we also have asteroseismology, unfortunately not in the bulge. So in Queiroz et al. 2020, we did run Star Horse with spectroscopy, Gaia, and photometry, and we show the very much impact of apogee. Here you see several surveys, distribution in high from the middle plane and the galactocene distance. And you see that apogee is the only one to really reach the bulge and also cover very close to the galactic midplane. So this led us to first do this extended map of galactic chemical maps in the galaxy, and then making clear that in the inner regions we had this dichotomy. This is a slide shown in the SDSS collaboration meeting last year by Matthew, and where he highlighted our results. In the outer parts, you see the low alpha, which is interpreted as the bending of the thin disk in the outer part. So all the thick disk is really only the inner part. Now, in the meantime, we got Kepler and Apogee exquisite data, and we could, in Miroslava Chiappini et al., really get ages. Now here you are looking solar vicinity age. I'm trying to show you what we know about the alpha over iron ages at high alpha. And what you see here, apart from a degradé color at the low disk stars in low alpha values, which is radio migration, but the focus on the high alpha. The high alpha show very old ages. If you plot age versus alpha over iron, we have this very coeval blue points, which is the high alpha stars, very coeval. You have some outliers, which I don't have time to discuss here, but they are called the young alpha region. So we run some simulations that show that actually the posterior probability distribution function of the age spread of that population we have in the solar vicinity for the thick disk was compatible with a scattering age not larger than 1.25 gigayears to the 95% level. So that's very important. Did we see a gap in the solar vicinity if we think that the galaxy was formed by two main star formation episodes? I'm talking about the solar vicinity. We barely see it probably here. We simulate our data with Trilegal, and the uncertainties we have in this data set is 25%. So we really need to go to better ages to start seeing this if it exists. So we also computed for this sample the velocity dispersion of this population of thick disk stars. And we show that actually for the older stars, there is a jump in the velocity dispersion. It's not a continuous relation. Suggested that the thick disk and the thin disk are really two different components. This is solar vicinity. Now let's go back to the bulge. Here, I'm just showing now, again, the Queiroz et al. 2020 paper. By the way, Anna is on vacation and she is the PhD student, also had not seen her family in 2 years. So I'm here covering her work. So here is the plot you have seen, and above you see the kind of precision we have both in AV and in distances. What is important now, I want to focus here. This was also highlighted in the Apogee collaboration together with other papers like that were already discussed in this conference, like Rojas Arriagada 2020 that I invite you to see. Essentially, we see a very complex situation when you go to the inner galaxy. So this is some maps of what we see of what is our sample that we call bulge bar sample. And you see here down the very high extinctions that prevent you to see really very much into the inner parts of the disk. Still, even with Apogee, you miss data very close to the plane in the innermost 1 kiloparsec. This is again the same, but using an updated EDR17. Now, the fact that came EDR3 brought very good proper motions, and so we thought we could do better. Not only choosing distance to select the bulge, but we could use the proper motion to, because we were afraid that in the bulge, we know that you have extinction curves that maybe not all constant and the way we think. So we said, let's also not be fully believing our distance, let's use something else. And we use proper motions to cut our distance. And this is the red sample I'm showing here. But of course, when we do proper motions, we use this as information to cut part of the sample and get a more centered sample towards the bulge. We lose the stars because with proper motion, we have many Gaia stars in the very inner parts of the galaxy that we don't have Gaia stars, but we have Apogee stars. Anyway, once we do this, we have around 8,000 stars that we left with, and 10,000 if you use the EDR17. And this is what you have when you are with this sample, but now very close to the mid plane. And here you have the metal poor extension of the bulge that we believe are traced not by the stars I'm showing here, but by the R-Lyra and the metal poor stars. And you have wonderful talks here in this conference. Here we still see this gap. And in the metal ridge, we see something that is kind of old, maybe, because it's not all solar, it's above solar. So we decided then to think about one way you can think is like we had this simple toy model of chemical evolution where you, I had it, where you have the metallicity as a function of time. And if you believe the bulge and the thick disk form very fast and had a sort of quenching of 1 gigayear, This would be a model that would keep the metallicity distributions of both in the way we observe them. From photometry as well as chemical patterns, we now know that the oldest stars of the Milky Way are in the bulge. Some of the oldest stars of the Milky Way are in the bulge and in the thick disk. And I'm talking about stars that are older than 10 to 12 gigayears. So could this population that we are seeing in the thick disk and maybe in the bulge, and I'll show you in a second, be explained by all this clumping? Are these the stars that are left over from this clumping phase that we just heard also from Mirka talk? So if I take a model like this with this kind of very fast formation of bulge, and here I put a pseudo-halo just for you to have a comparison. And here I plotted the Bainsby et al. Stars, only the old stars older than 10 gigayears. You see that I make a model that more or less can have the bulge distribution, only the one distribution, the one that is not having a peak in the high metallicity. So I'm saying I'm modeling the old bulge. If I do this and I compare the old bulge with the halo, I have this kind of model, which is a stochastic model. And then I can see, for example, these stars here is, for example, one of the stars from Bainsby that is a high metallicity, but is also very old. So here, these big stars are only the Bainsby stars very old that I'm plotting here. Here are some halo stars for which I don't have age. We have other, we show other chemical evolution models, for example, from Frias and Barbuy. This is also showing some relations. But you see that if you go to individual abundance measurements in some windows in the Milky Way, you get a lot of dispersion here. So we can apply this stochastic model also to other elements, and we showed this in the review, and we predicted that the bulge, the oldest bulge stars are around here, -2 to -1.5. And we kind of have a model that if you form like this very fast an old bulge, you kind of fit the data. Now, this is more or less the metallicity range also traced by the Brava stars that were shown by Andrea Kunda. Okay, let's get back now to this part. So is this blob that I'm seeing, the apogee data, the old bulge? Is this the thick disk? Can I differentiate them in age or in chemically? And in the metal rich, what exactly I'm seeing? So we have been seeing these conference 7 metallicity distributions. For example, the one of Rojas Arriagada, which is showing these 2 or 3 populations, but also the one in physical space shown by Mike. And here also, if I take our bulge bar sample or the RPM, as we call the sample that is based on proper motions, you see you have different components. But can we do better? So what we did, we took this sample that are more concentrated in the inner part of the galaxy, and instead of using a chemical cut or a kinematical cut, which are all dangerous, we just look to the sample on, we compute the orbits for these stars. Yes, it's dangerous because we don't know very well the potential, but we did compute the orbit of the stars. And we project the stars into a Zmax eccentricity plane. So the maximum height of the stars in the orbit versus eccentricity. First, and we divide it in families, A, B, C, D, E, F, G, A, I here. First of all, in metallicity, you see clearly a gradient that the stars that have Zmax larger than 2, they tend to be more metal poor, and the more metal rich are here. But it doesn't mean there's also not metal poor stars here. And that's what we're gonna see right now. So if you open this diagram and now look for each of these orbital space, so you look to the chemical properties, you see the alpha over iron ratios, and you see, for example, that here in this last diagram, very eccentric, but very confined to the midplane of the galaxy, you do have this very high metallicity blob, but you also have the high alpha stars. And you start seeing something weird that when you go here, I put this thing here so that you see what I'm talking about. You start see that there is an excess of high alpha, high metallicity stars here, where this is not seen in, here you see a little bit in the second one, but here, and I'm now walking lower eccentricities, you see less of this. So it's like if you are moving from a thick disk to something else when you go to larger eccentricities. So we can check more what exactly the properties of these stars. The metallicity distribution in this plane look like this. When you are here low, you have a typical inner thin disk, which very high metallicity. And here, the high metallicity go even above 0.2. That's very large metallicity. In between, you have something that look more like a thick disk. I hope you're seeing my cursor. And in the upper part here, you see something that's very high velocity dispersion, of course, because that's how we define it, but we see the chemical characteristic of the high velocity dispersion stars. And you see that this metal per component was already present here low and goes up and is around the minus 0.7. You can look as if you want the velocity dispersion of these components. And in fact, the one that had the MDF similar to the thick disk has a velocity dispersion similar to the velocity dispersion we saw at the solar vicinity. While here you have another component which is very high velocity dispersion. Now we did another thing. We compute the orbits, the probability of a star to be in a bar orbit shape. And the larger the probability, the red the point is. So you see that most of the stars in bar orbit shape are here, but still they show, of course, they show in both high and low alphas. And here again, you seem to see that the alpha over iron are extended to large metallicities when you are in this component. So is this the old bulge? Is this the coalesced migrated clumps? That's my question to you, but that could be that we are starting to see the old bulge. Here is more or less the guiding radius of the star. So that population is really traced in the very inner parts of the galaxy. So to conclude, I would like to say that the Milky Way properties are showing us now new constraints. We, from the kinematic data dissected on eccentricities in max plane, we now see several chemical kinematical signatures that show a bar, an inner thin disk, metal rich, an inner thick disk, but also a broad metallicity population with large velocity dispersion, indicative of a pressure supported component, and an extended alpha over iron plateau. Very old chemical thick disk is something that we see in the solar vicinity, and we may see a gap. We see very old in situ metal poor stars component also in another paper that I didn't have time to discuss. And the chemical evolution models that assume a very short time scale formation can fit, are compatible with chemical abundance in general. And also we have other CMD work showing that the bulge is mostly old. We also have very old traces, as we saw, and globular clusters and debris as well, as I didn't have time to show you. We see an inner thin disk, which has a peak metallicity around the 0.2 dex and a bar that is even more metallicity of around 0.25 dex. Points for discussion. We are, in my opinion, we are just discovering our own bulge now. And so we are dissecting this bulge in the physical and orbital space, something we could not do before Gaia, nor before Apogee. So I think but I put as a question, is it too early to discard a very old pristine population in the Milky Way? My answer is yes, but of course others may say no. How old can this pure bar disk scenario be in place? So you can explain, some models want to explain the whole thing we are seeing as disks, either a bunch of thick disks or thin disks, but how old can these things form? I'm talking about ages probably older than 8 gigayear here. I'm talking about things formed in redshift 2 at least, if not larger. So we know that there is a strange double star formation probably in the solar vicinity. Can the clumps then offer a way to form this pristine old bulges? And then do they have an explanation to truncate the thick disk star formation history and the bulge star formation history? And of course, as everybody will finish saying this data is not enough, because you saw after all this, we had 8,000 stars, so it's not enough. Have the referee complaining, oh, how can you do a distribution with 200 stars, whatever. So we need more data. And we have to cover this part of the galaxy. See, this is, again, the data of Kairos, and we need the more data in this part, in the south of the galaxy. And that's what we are doing with the foremost low resolution. If you are in one of the institutes that you can join for free, just come and talk to me. If not, come and talk to me and we see if we can arrange something. And for the future, for the young people here, but really young, for the 2050s, we have proposed 2 projects to go for the ESA Voyage 2050. One project is called HEIDIN, which is to do asteroseismology in dense fields, maybe in the bulge area and also in globular clusters. And the other is the Gaia near infrared, which is Gaia near infrared. There is a lot of problems in how to make the instrument for doing that, but they are in study. So you please, would be nice if the community would join us in this effort. Thank you.
Thanks a lot, Cristina. It was very, very nice. And especially given the condition, the COVID and the problem. Thanks a lot. Do we have questions? I guess Mike and then Francesca. Please, Mike.
Very nice talk, and congratulations on your recovery and being able to give your talk. So I had a couple of concerns about, I've had long-standing concerns about this K-Rose data set and this gap between the alpha-rich and alpha-poor stars that isn't seen, say, in Rojas Arriagada and other optical alpha to FE versus FE over H. And I'm just worried about it. I wonder if it could be an artifact of the training sets used in apogee.
No, yeah, I understand this. No, it doesn't.
I'm really worried about it. Yeah.
No, we are plotting here a kernel distribution. Of course, if you plot the points, you're not going to see this so clearly. But this is not a novel. In some sense, for the bulge, you had already Rojas Arriagada 2019 using another release of Apogee, which was already had to do a more job, but was already seeing this. Here is just becoming more clear. And the duality in the solar vicinity is now very robust. You have all kinds of data. In the beginning, we thought
in the solar vicinity, I fully agree with you. I'm just worried about the bulge because, like,
okay. So that's why I say we are very worried about the bulge and very worried about our distance in the bulge, right? Yeah. But for example, there is another paper recently by Hogg using a different way to do things and using division with actions. And still there is 2 populations. So I'm not seeing this as I don't find a way to find any kind of obvious thing to produce this. I thought in the beginning what was happening, that's why I wanted to open it in orbital space. I thought in the beginning we were seeing on one side only the thick disk and the other side just the disk. And the distances were not correct when we are very much to the disk because, we are using a simple law. But so far, our distance have been tested by several groups and used for several other things. For example, for Sagittarius, we are producing a paper now on this. But it can be, Mike, I don't put my hand on fire here. But what gives me some confidence that for the solar vicinity, there is.
I worry the optical analyses, the optical high resolution analyses in the bulge don't see such a sharp gap. But that leads to the second question was, in your orbital analysis, did you consider restricting your analysis to just red clump stars where the distances, there's an independent, estimate of distances? Did that change anything?
No, we didn't do this.
Just the red clump.
Yeah, so my thing here is that we had so much thing to do because we had also 2 releases for Apogee to do. But what we did is like we publish everything. So all the data is public, is in the VEC of DR16 and DR17, our data. So everybody can take and can play with it and see. If you don't find, just let me know.
Okay. No, thank you. Very nice talk.
Thank you. And in any case, we will have to wait not much longer, right? Once you have foremost, you have all your optical spectroscopy.
I also worry about the fact that when I did the review with Beatriz and Gerhard, and Ortwin, we wanted to see also the abundances in these low extinction windows, not the Gibbs and so on. But the fact is, even the Gibbs, probably you don't see exactly this dichotomy there because it's few stars, but you see a double metallist distribution. You see that, okay? So there are two components. Now, if they have a gap in between the two of them, if they have less gap, this is the discussion which also we had for 10 years in the solar vicinity. So it's gonna probably continue 20 years in the bulge.
Hopefully not. Francesca, you raise your hand or yeah.
Yeah, I don't know. Is there still time? Should I ask or keep it for the discussion?
Just keep it short, then ask your question. Yeah.
Okay. Thanks a lot for the great talk, Cristina. Thanks so much for giving this. So I was wondering in the old kind of spheroidal population you were mentioning, is this a distinct, first of all, how metal poor is this population? I think you might have mentioned, but I missed it. And is this distinct from like the inner halo? Would this be a distinct population from the inner halo?
Yeah, so the population I'm showing is a population that is peaking at a metallicity of -0.07. And so it's difficult because we want to, what do we want? We want to say if it's thick disk or if it's a spheroidal, right? So this population, there is a population of stars there that have a very high dispersion, velocity dispersion, is above the thick disk. Mm-hmm. And it seems, and I see this result as marginally because that's the data we had, but it's something that I would like that people play more with the data and try to look. It seems that if I go to this window, see the windows of the high eccentricities, I see an extended plateau a bit at larger metallicity. Well, from chemical evolution models, that would be what we would expect. If the bulge has a star formation efficiency if this component, has a star formation efficiency larger than what you have in other components, you would extend the plateau to larger metallicities. Is marginal because that's a very few difference we are finding. And also the models are run for fitting the chemical evolution of all the stars in the bulge, assumes the same IMF that here. There is also this complication. But why I assume same IMF? Because I still didn't see the difference in the plateau between stars that are thick disk or something. They are all at the same level. But
these are not halo, these will not be considered halo stars because they're too alpha enhanced, or?
Yeah, they are too alpha rich. They are too metal rich. So they are -0.07 peaking there. And these are, I'm showing you Zmax. So the maximum high in the orbit. So it's really like stars that are below 3 kiloparsec.
Mm-hmm. Okay, thanks.
Okay, thanks a lot. Thanks again, Cristina. We can move to the last talk of the session. Oscar Gonzalez is going to talk about the Milky Way bulge, but from a future perspective. So in the JWST and ELT area. So yeah, Oscar, I'm going to give you the 3 minutes warning. Okay. I think you're still muted.
That's correct. I was still muted.
Okay, all right.
Really, no.
It's fine, the 3 minutes warning.
That's totally fine. Thank you very much. Perfect. So thank you very much, first of all, to the organizers for inviting me to do this. Also to for the format of the meeting, actually, given the fact that I'm the last one to speak, I think it's a good chance for me to thank you for the format. It has been very flexible and allowing us to participate, despite the fact that it's quite late here for giving the last presentation. But and I have the task of giving you the future perspectives of the Milky Way bulge science, and this is particularly a nice thing to do after the nice review from the nice overview that Cristina just gave, and the discussion that we just had, because it highlights that despite the fact that we have achieved quite some significant progress with the recent surveys, there's still quite a lot to do. And my job in this presentation will be to show you that the future will likely give us more data that we could possibly know what to do with. And it's a good time to do it because in a meeting like this one, we require the feedback from the expert simulation experts, as well as extragalactic bulges, so that we have the time to fine-tune the strategies for these surveys and future instrumentation requirements as well. So I will start with that. I mentioned requirements because this is particularly important for the case of studying the Milky Way bulge. So I'm showing here this nice density plot from Chris Wegg from 2015, where he combined red clump star densities using different infrared surveys that cover both south and northern hemisphere. So you can have a nice view of the overall density in the infrared of the red clumps in the bulge and the bar and the inner disk. So we have heard throughout this meeting the wide variety of results that point into different components, where components I'm not necessarily talking that they do have different origins, although we can see that might be the fact. And different results point to different origins and different formation histories and evolutions for these different components. And in order to do that association, what we need is fantastic data. And of course, accessing that data requires a combination of both imaging and spectroscopy that with a wide range of capabilities, given what I'm going to be showing now on how different it is to access these components throughout the overall structure of the bulge. So we'll start with the photometric surveys. I'm obviously not going to give an extensive summary of the past surveys, but I'm going to be trying to focus on the present and moving forwards in the stage in which we are. So I'll start here with the outer regions that, of course, is no surprise to everyone that they are nicely accessible to optical surveys, which is fantastic. We're talking about everything above 2 degrees in galactic latitude. And here I'm highlighting two very nice surveys. One is the Blanco Decam bulge survey, and of course, the forthcoming LSST, the Vera Rubin Observatory, that will become for sure the reference surveys when looking at multicolor, and in the case of LSST, of course, multi-epoch photometry, all the way down to the main sequence turn-off throughout the entirety of the other bulge. And of course, this, when coupled with the Gaia information, it's a fantastic data set to have access to. So I'm showing here an example of color magnitude diagram there from Chris Johnson's paper in 2020, and the layout of the field coverage of the case of BDBS survey. I would like to point out here, this is very exciting thing to see. In fact, that BDBS does provide photometric metallicity. This is something that has been highlighted by Mike Rich throughout the meeting, and I invited you to see his talk as well for references and the details on this. But what I'm showing here is that the access to the U-band photometry allows you to calibrate with the color of human's eye, the reddened fields across this entire footprint to have a nice correlation, a nice calibration with spectroscopic metallicities from the Gibbs survey. And this is a fantastic tool to have to look into the overall metallicities. And it's we're looking at this to within 0.2 dex, so it's very exciting. Then moving closer into the midplane of the bulge, that's where, of course, near-infrared surveys are necessary in the case of photometry to allow us to map the entire bulge, so including the bar down to its full extension. And of course, here, when we start entering into limitations anyway with the infrared surveys, this comes from the very high stellar densities as we start going into closer into the innermost parts of the galaxy. Here is where much higher spatial sampling starts being the key requirement for better source deblending and reaching the necessary completeness that is required for very nice statistical studies all the way to the main sequence turn-off near the galactic midplane. I'm showing here two examples of a relatively outer color magnitude diagram from Francisco Surot's paper. This is PSF photometry from the VVV survey. You can see the nice features in the outer field, where you see nicely the red clump and the photometry going all the way down to the main sequence, and then you see the strong impact of reddening in the left color magnitude diagram as you move closer to the midplane, and completeness starts hitting you much severely, pretty much at the level of the right below the red clump. So, of course, this, as I was saying, this becomes even harder as you go into the innermost regions. So what I will call here as the nuclear bulge, composed by the nuclear stellar disk and the nuclear star cluster. and of course the inner parts of the bulge itself. And here, because of the very, very high densities, when you start trying to get into the fainter magnitudes close to the main sequence turn-up, you're required to even finer sampling scales that are no longer available or accessible by seeing limited, in which case we need the diffraction limit provided by space telescopes or adaptive optics facilities where they become fundamental. And I'm showing here a nice example of a recent survey data set called the Galactic Nucleus Survey. This is well, there is a variety of papers with very, very interesting results mapping the central 200 parsecs of the Milky Way. This by Nogueras Lara in 2019, and the color magnitude diagram there of the very central most field, where you see that the levels of completeness down to the main sequence turn-up are well below the 50%. Despite the fact that at the level of the red clump, it is a fantastic data set, and it's the deepest data set for near infrared with relatively wide coverage of these innermost regions. So now, that's for the case of photometry. So now I want to show slightly how things go when we go into the spectroscopic surveys very quickly. I started to make a kind of a composition of the different footprints of the different surveys until I remember that Andrea Kunder had made this beautiful diagram already in her 2022 review of our Lyra stars. So thank you very much, Andrea, for that figure. Is really a relief to have it. You can see there the footprint of all the spectroscopic surveys that now are available, including Argos, Apogee, Brava, Gibbs, and of course Gaia ESO as well. And you can see that it covers very nicely with different levels of patchiness, let's call it that way, different densities across the different galaxy, all the way to the center by Apogee, which composed the nice results that were presented before by Cristina. So these existing surveys focus on red giants, right? We're talking red clump stars. Depending on where you are, the selections are slightly different. Red clump stars, K-band or M giants for the case of Apogee. Samples vary, of course, as well, depending on the survey and the location of this. We're talking about the 2,000 to 20,000 samples, as you see there in the figure, with the typical order of 100 to 300 stars per field, with varied fields of view depending on the facility, ranging from the 25 arc minutes of flames all the way to that should be 2 degrees in diameter. And now, once we move into the new generation of surveys, where surprisingly enough, I mean, not surprisingly, but really exciting to see the fact that we're not probably going to be looking so much into patchy footprints, but we're going to start looking and pushing these facilities to create contiguous fields of these different regions. So I'm showing here the examples of the areas where these different facilities will actually shine and do the most of the hard work on providing such data sets. So foremost in the optical 4-meter telescope in the Vista facility will be covering very nicely the overall bulge outside of the midplane. And in the midplane is where we will have SDSS 5, the Milky Way mapper, doing a fantastic job there, and moons piercing through, pushing the red clump star samples all the way to the far end of the bar. Here, the number of stars that we will be looking at are really striking. So we're now talking about 500,000 to 1 million samples into the service covering all these regions. Each field will also statistically get much better sampling, 300 to 2,000 stars per field, with similar fields of view of what we were discussing before. So the huge jump in terms of sample statistics for what we're talking in this meeting quite a lot, which is the statistics and to the population decomposition, to really understand and decouple the different components that are composing the inner parts of the galaxy. It's going to become fantastic, and we're going to be able to do this with very nice field mapping with contiguous fields. I'll show a few more details as well. And of course, not only the central part of the bulge is what we will be looking at, but let's not forget that we're also going to be able to map the inner disk transition and the bar all the way from to the far end by moons, reaching again with red clump stars, and the near end with WEAVE in the north with the low resolution disk galactic archaeology survey. So all of this is very exciting times of the facilities that will come in what I call the imminent future, right? This is the immediately next generation facilities that are coming. I want to highlight just in one slide this for the the nature of this meeting, and it's something quite close to my heart, which is the importance of spatial sampling when looking at this data. And what I mean with the spatial sampling is, let's say, the volumes in which we're selecting samples to do this population decomposition in the bulge, and how do they compare? How do we put them in context, in an extragalactic context, let's put it that way. So what I show here is the beautiful WISE image of the bulge, where you can pretty much see the boxy pinage, if not the X shape of the bulge, directly from Melisseness and Lank in 2016. And one of my favorite galaxies is, some of you know, NGC 4710 with that beautiful X shape contours that you can see there. So when we consider that at a distance of the order of 20 megaparsecs, right, which are typical for this for surveys such as the timer survey from that I'm showing here, an impressive map of kinematics and populations from this survey for a variety of galaxies and inner regions of these galaxies from the timer survey from Dimitri and his collaborators. So when we think about that, right, when we see the one arc second corresponds to the order of 100 parsec spatial scales in what we're looking at in these external galaxies. In this case, VLT Muse has, we know it has 0.2 arc second spaxels. So each spatial sampling is 0.2 arc seconds. And these are sampling a full width half max of the order of 0.6 to 0.8 arc seconds. So when you do that calculation, you can realize that in the case of the Milky Way, right, we're starting to now see, when we do contiguous fields, in the case of moons, for example, with a 25 arc minute diameter, 900 stars, or twice that when we do two visits, gives enough statistics, right? We're building samples to within spatial beams that are nicely comparable to the scales that are mapped by these extragalactic surveys. And I think this is a very, very nice tool to have, in which we're able to do population decomposition at these scales with impressive amount of detail to then feed to what is being observed in these external systems. So I do consider this to be a very, very nice, a very important requirement for these surveys. So as we start digging into the center of the Milky Way, which we start thinking about the topic of actually my talk, which is the JWST and the ELT era, right? That's where these new facilities will be undoubtedly start to really shine. So as we start going deeper into the galaxy, what I just discussed now, we look into where these 4 to 8 meter spectroscopic facilities will produce fantastic data sets. However, there are a few things here that these facilities are yet unable to do. And one of these is to in fact, to reach the deep magnitudes that are necessary to trace spectroscopy of main sequence turn of stars that provide very, very accurate, nice stellar ages. So I'm just showing there the magnitude cuts of the Milky Way mapper. Of course, there are many more stars above a magnitude of 11. It's just that BBB suffers from saturation there, while Moons is able to trace, as I was saying, the red clump all over the galaxy. And you can see the importance of doing this, of being able to have spectroscopic ages. Apogee has done a great job here, and I'm just showing one example of this, where they collected a sample of ages for 6,000 stars distributed across the entire Apogee region. And of course, you saw the very nice results from Cristina before as well. So doing this exercise is very important. But what I'm talking about here is reaching the very, very high precision ages that are available. For example, the ones that are being seen by the microlens dwarfs from Thomas Bensby and collaborators. So that's the problem. And unfortunately, even though moons can do this with quite long exposures of the order of an entire night, this requires, of course, a very deep multi-epoch photometry to be able to successfully allocated the fibers into these stars, avoiding foreground stars from the disk. I invite you to see Tommaso Marchetti's talk. Of course, you probably already have seen it, where he talks about the decontamination techniques that are important for us to be able to see this main sequence turn-off stars. So as we go deeper into the galaxy, right, I think that when we enter into what I'm referring to here again as the nuclear bulge is where the JWST and ELT will do their first very, very strong impact, right? We know that the nuclear bulge is the very most dust obscure region, complex region of the Milky Way. Different components are present, coexistent there with the formation histories that still remain with many, many open questions that need to be understood. And critically, these populations need to be dated throughout their entire populations. You can see the talk from Jason in terms of the importance of dating and his technique to do this in these regions with MIRAS from the VVV survey. So as we go into the central, say, few parsecs of the galaxy, that's where seeing limited stars, seeing limited facilities are no longer capable for us to allow us to reach these very faint stars. And this is where these facilities, as I was saying before, space telescope, JWST, and of course the ELT facilities will start to giving us access. So I'm showing here a couple of very exciting examples of
left, Oscar, sorry.
Perfect. Yeah, of some exciting data sets that are about to come. We're talking about here about the first example here is a mapping with the NIRCam, which is this imaging, near infrared camera imaging from JWST with a field of view that I'm showing here as the footprint of nearly 2 fields of 2 arc minutes with very nice sampling of the order of 70 mass sampled with 2 pixels. And there is a program already for cycle 1 that you can find some details on the program pages that will be mapping the central 2 arc minutes of this region, reaching proper motions by doing a multi-epoch observation that will reach all the way to K band of 20, right, with a 0.5 milliarsecond per year precision. So this is fantastic stuff that will be happening. And we're talking about the very central 2 arc minute region. Then when we consider as well other facilities that are available, JWST, that is near spec, the integral field unit spectrograph, in this case with a smaller field of view, rather a slightly bigger spatial scale, but enough, more than enough, indeed, to map, in the case of this program, for example, central 9 arc seconds of the nuclear bulge to be able to determine radial velocities and metallicities from low resolution spectra of the order of R of 3000. So I'm showing here just an example just to show you the jump that this facility will allow us to do. You know, here's a comparable field of view K-band image taken with VLT NACO from Shuttle and collaborators in 2020 down to similar magnitudes. Now what we're talking is that NearSpec will provide spectroscopy for all of these sources, which is absolutely mind-blowing to think, in my opinion. And of course, reaching these very faint magnitudes is critical for what I was saying before, because as fainter magnitudes you reach, it's where we know that the old stellar populations are actually dominating, and we're going to be able to trace and characterize these populations accurately and in a complete manner in these very, very interesting regions. Now we do the jump to the ELT, and I'm showing here as an example of what this facility will open, which is absolutely fantastic if you start thinking that we're going to be able to reach similar limiting magnitudes, so similar sensitivities, but with almost a factor 6 improvement in the angular resolution that Mikado will be able to provide. And you see there a nice comparison of the different facilities. And of course, in this case, in the very near vicinity of the supermassive black hole of the Milky Way, we'll be able to obtain very accurate astrometric measurements with an unprecedented resolution and depth in the vicinity of this, of the supermassive black hole and in the vicinity of the nuclear star cluster. And the last one that I will mention is HARMONY, right? Of course, HARMONY is the integral field unit spectrograph for the ELT, in which case it will allow us to now extend, similarly to what I was showing before with Mikado, but now providing as well a spectroscopy for all the stars down to the levels of the main sequence turn-off with a high resolution, with resolution similar and comparable to the surveys that I was talking before. We're talking about a resolving power of 18,000 for the main sequence stars, all the way to the center of the nuclear star cluster, which is absolutely fantastic and exciting to think on what we will find. And I'm just gonna skip this because I'm just showing the examples of what I was saying before. In amazing times, you know, an ELT harmony will be able to achieve this in a few hour exposures compared to the existing surveys. Going out of the center of the galaxy, and this is my last slide, Elena, sorry about this, we will move into the multi-object spectrograph, so mosaic for the ELT. Now we're talking about multiplexity with a fiber-fed spectrograph, and as well as a deployable IFU with a multiplexity of 200 or 100 in the infrared for the fiber-fed, and of 8 for the mini IFUs that are deployable in a field of view of the order of 3.5 to 4 arc minutes. All right, at again comparable resolving powers of 18,000, allowing us to reach main sequence stars now anywhere in the bulge where we are interested to do it. And don't forget about, of course, about ANDIS, the high resolution spectrograph, a very high resolution, 100,000 resolving power, allowing us to follow up individual stars with very, very high accuracy to follow up critical targets across the bulge. Again, I want to highlight here that this kind of facility, fiber-fed facilities, are indeed limited by the target selection of these main sequence external stars to fit the fibers, right? So this is one critical thing that we need to start working on to be able to do this sort of fantastic science that will be coming up. So I will leave here the summary of what I've just said. I won't go through the summary again, but I do want to put these questions up for discussion that I've mentioned throughout my talk, which is like, if we have some fields to do these very accurate studies across the bulge, we can no longer, with these amazing facilities, we no longer have the capability of having full coverage. So we need to be strategic in selecting the right windows in which we want to do this very deep, very accurate characterization of the populations. So where do we look? That's the question for the simulations, and from, of course, from what we know from extragalactic surveys. And the last one is, of course, that we do need to make sure that those samples allow us to improve the larger samples of red giants provided by the different spectroscopic surveys across. And what do we need to do to ensure that happens? So I will stop there. Sorry for the extension, Ellen.
Fine, Oscar. Thanks a lot. Do we have a question for Oscar? Let me check. That was an applause from Francesca, from Cristina. Any question? Let me see. Since not, I do have a question.
I see two hands up.
Yeah, sorry. Francesca?
Yes, thanks, Oscar, for this great review of what's coming up. It's really exciting. I was wondering, maybe you have some thoughts on the question of where to look in the bulge, you know, with these surveys, these upcoming surveys, in future facilities. What would you say is kind of the key places to look to answer some of the key questions we still need to answer? I'd like to hear your thoughts on that.
Yeah, I think it's my side of the answer will come from the new spectroscopic surveys. You know, once we start observing with you know, the new generation of surveys, foremost with MOONS and Sloan 5, I think that will open up regions that are very interesting, in which we would like to see further into the Milky Way. My question kind of comes to, it's to you guys, it's to the simulators, into what areas do you think that we should, that contain the most of the information that perhaps we don't know yet and will not be visible by these surveys. And similarly from you know, surveys like the TIMES survey, when you see these very particular properties and varied properties in the inner regions of these galaxies. So it will be really interesting to make that connection and make sure that we access the critical parts.
Yeah, maybe to very briefly answer it, I think, you know, with moons, we're going to be able to probe really the inner, close to the plane and the inner galaxy where we haven't seen much before. So I think that's going to be a really exciting place to look in the future.
Yeah.
Okay, thanks. Yeah, Mike, try to keep it short, please, because you're really
great talk. Very exciting future. Just to say that I think the chemical evolution models will, you know, have to improve to keep up with the amazing flow of data that will be coming. So, and that will, you know, they'll have to consider not just Gaussians, but, you know, very complicated pictures of chemical evolution. That's all.
Thanks.
Yeah, I completely agree. Thanks, Mike.
Thanks a lot again, Oscar. It was a very, very nice talk, as well as a talk by Mirka and Cristina. So before we go in on a break, please hold 1 sec longer because we would like to take a picture as we have done this morning. So if you can switch on your camera for us, and Francesca's gonna take the photo.
Yes, I still see cameras turning on, so just gonna give it a minute. Good. Okay, so let's do the same as before. So on 3, everyone say bulges. Hold it for a second. Keep smiling. Wonderful. Thank you, everyone.
All right. So as I said, we are running a little bit late. So but we're gonna have a break. Let's do a break of 10 minutes. So now it's 8:30. So we will convene at 20 to 9 sharp. So we will have Livia and Bruce leading the final discussion. See you in 10 minutes then.